All right, this will just be a short video kind of discussing the models and the connection to the problems. Did you look through those questions? Did you see which ones might be more focused on place value versus friendly number strategy or composition or decomposing? Or I said composition, I meant compensation, or just the standard algorithm. Um, like I said in the earlier video, there's always that question, well, if we teach all of these to our kids, won't they be confused? Yes, yes, they will. The idea isn't necessarily to teach them. We pull this from their heads and we help them advance to more sophisticated um, models and representations. So let's go ahead and take a look at some of these. In first grade, students begin to develop the idea of tens or tenness. This understanding emphasizes the importance on the various place values in our number system. The early use of base 10 blocks and representations allows students to transition to expand to notation models, such as the traditional representation where, for in this example, both addends are broken apart into tens and ones and added separately. So let me get my pen here. So right here, we break them both into tens and ones. We can also see that in the base 10 model. Here's our tens, and then here's our ones. And when we put them together, we put our tens and ones, our tens together, and then our ones together. And what's cool about this is students can see I can actually do either first. I don't always have to start in the ones place and work over. I can add my tens together and I can add my ones together and then I put them all together. Some other models like this tree diagram, that's what this one's called. The tree diagram, um, partial sums, the traditional algorithm, all use the same idea of adding tens and ones separately before combining the parts to get the final answer. As the process becomes more efficient, students may be aware of the continued place value needed to solve these problems. Teachers must ask the questions to ascertain the depth of student understanding. So if we look at this tree diagram, it's the exact same as what's happening over here, where I'm taking it's just a little further on that continuum, moving towards abstraction, from concrete to abstract. So I'm taking my 60 and my 40, and then my 7 and 8. I'm just not writing it out in expanded form like I am over on the left. And then let me clear my screen here. And then this model here takes it one more level in that abstraction. Now, I probably should have sorted these so that they were in that progression. I just didn't. But we can see 7 plus 8 is 15. 60 plus 40 is 100. And when I add those together, so that when I get to the final traditional algorithm, I can still see my 15. There's my 10 and my 5. And then I have 11 tens, which is 110. When student strategies employ breaking up numbers not based on place value thinking, a number line or arrow language may be a good way to represent this thinking. These models usually maintain one of the two addends and then decompose the second addend. The students initially begin with less efficient models and develop more flexibility as they gain experiences. The use of number paths naturally lead to the use of closed number lines. And that's with all the hash marks present. And eventually to an open number line, which is like what you see on the right here, that with not all the hash marks present. A natural extension from open number lines are what we call arrow language. And we want to be careful to not use the equal sign because it's actually misusing it. So if we do 67 plus 3 equals 70, plus 30 equals 100, plus 10 equals 110, we're actually misusing the equal sign. What it's saying is, after all of this operation, 67 plus 3, and if I used equal signs, would be equal to 115. That's not accurate. So to get around that and not abuse the equal sign, we use arrows. And really all it's doing is showing the jumps on a number line and removing the number line. Contexts which naturally support the use of these models are those involving linear measurement. Rulers, tape measures are a type of a closed number line. Problems involving length, elapsed time, temperature, or money tend to be really good contexts for these types of models. Once students understand the model, they're able to apply these in other situations. Compensation is a strategy where students change one or both of the add-ins to make the problem easier to add. When students find the sum of this easier problem, they must either add or subtract again in order to find the actual answer. Students must have a strong number sense in order to efficiently use this strategy to solve problems. Compensation is often taught or shown to students directly, and then students practice it. This can really lead to some misunderstandings of the process because unless students understand the benefit of using this process, it feels really unnatural. The strategy can be done symbolically, which I've shown here, or with number lines where a student may overjump a number and then have to come back. Model selection mirrors student approaches to a problem. Given a bare number problem, students may choose the strategy of either decomposing the numbers, which is breaking them apart, or compensating the numbers, which is changing one of the numbers to make it easier and then adjusting it at the end. Decomposition models can often be done by breaking the number by place value or may focus on decomposing based on the given numbers in a relationship between these. Compensation models tend to be based on the given numbers and should be an intuitive process to the individual solving the problem. Students need to practice to develop the number sense required for this strategy. The standard algorithm is efficient but can obscure the math structures that are being used. Although this is a decomposition strategy based on breaking the numbers by place value, it's not always clear to students.